task, work on video. Video 3, geology. In this task, you should work on video. The theme of it is geology. To work on the video, a video segment from the YouTube channel Earth Science with Adrian, etc. was used. How to get the job done? Listen to the passage 3-5 times, making notes in your notebook and adding new details each time you listen. After that, make up a story and write it down. Send your entry for verification.
Here we are on the Earth as scientists, trying to figure out patterns, cycles, and the details of the world around us so that we can feel like we're in control. We work to build civilizations and try to make things nice and clean and safe. We use pretty rocks to build things, smudgy, dirty rocks to stay warm and go fast, and soft, muddy rocks to make other things. But there are volcanoes that occasionally destroy everything, earthquakes that destroy everything, and landslides that destroy everything. And this is why we can't have nice things. The people demand safety. They demand a hero to save them from the crazy things that the earth throws at us. That hero is a geologist. I can tell that I've already sold you on geology, and before you open a new tab to get on the college website and change your major to geology, which I'm sure you're all going to do, you need to make it through Geo Bootcamp first. You've got to earn your rock hammer, and step 1 is to learn the basics of geology. Like, what is it that geologists actually study? What is the geosphere? Well, we don't really study the things in the sky, okay? The atmosphere is not the geosphere. Not exactly, but more on that later. We let our atmospheric scientist buddies handle things like weather, air currents, circulation, greenhouse gases, and the like. But atmospheric scientists are Earth scientists, and we work together pretty regularly, especially if you do your research in something we call the cryosphere, which is the frozen Earth. However, we need to keep looking because the atmosphere is not really geology. So what about the ocean? Well, oceanographers are pretty deep as far as scientists go. And we let them handle all the research on the ocean's currents, temperature, chemistry, and physical properties so that we can handle the heavy stuff. Oceanographers are also Earth scientists, and we love to work with them all the time. But the hydrosphere isn't really the geosphere. It's too soggy. The complex and beautiful world of biology. Now, I have a lot of respect for biologists because life is hard, and it can be pretty hard to study. Plus, the biosphere is something that makes our little rocky planet unique from all the other planets we've known so far. But the really cool thing about geology is that you can be a geologist on other planets too, because they all have geology, even if they don't all have life. Geologists and biologists do work together all the time on things like paleontology, soil science, but really, geology is impactful on life and vice versa, but the biosphere isn't geology. It's just a little too squishy. Okay, the cryosphere. We're starting to get to some geology. Like I said before, geology is the study of the solid Earth, and ice is pretty solid stuff. The other cool thing about ice is that it is the mineral form of water, and geologists definitely study minerals. The cryosphere is held a little separate from what most people would call geology because water is such a special thing. But the cryosphere is still part of geology. Here we are, definitely geology, right? Look at all of that beautiful geology. We're definitely in geology land. We've got rocks, mountains, glaciers, erosion of said mountains by said glaciers, soil, and all kinds of geological stuff. Now, I want to make a caveat that this whole solid Earth business, right, is a little bit complicated, right? Geologists are interested in some pretty important semi-solid, squishy, solid, or semi-liquid stuff, okay? So, for example, imagine a volcano. Go ahead, imagine it. I'll wait. You got it? Okay. Now, I'd put money on you having imagined an erupting volcano. You did, didn't you? Well, I can hear you thinking to yourself, Professor Sorensen, you said geology is about solid things. Lava is not solid. Well, okay, so let's take a look at that. It looks like it's flowing, so that's a point for the lava being in a liquid, a camp, okay? So if we took a super close look at that lava, though, we can see a ton of tiny little crystals floating around in there. Look at them go! Magma and lava, which behave very much like a liquid at times, are not 100% a liquid. In fact, it's actually a viscous, semi-solid mineral mush, if you will. Or you could say that it's molten plastic rock. But the bottom line is that we can definitely classify lava and magma as part of the solid Earth because we've got all those little solid chunkies in there. Okay, so here is our world. Most of our planet is just plain old geology. We live on a rocky planet that has a two-part iron-nickel core. The inner core is under so much pressure that even though the temperature is so ridiculously high, the gravity of the planet compresses it into a solid. The pressure lets up a little bit for the outer core, which is a liquid, because it is so ridiculously hot. Then there's the mantle, which is high-density superheated rock material. Okay, the difference between the mantle and the core is that the core is made of metal and the mantle is made of minerals with some metal thrown into. Most of our planet is the mantle. See that thin, tiny little bit around the very outside of our planet? That's our whole world. That's that tiny little sliver. That's where we live. We call it the lithosphere. And all of the continents, oceans, cities, and life of our planet is there. Our class is going to focus on the lithosphere. Now, the lithosphere is not all geology all the time. There's other stuff up there too that affects the geology of our lithosphere. So let's get a fuller picture of how our solid Earth works. So we're going to need to take a field trip to the liquid, gas, and squishy parts of the Earth that we talked about before. Now, atmospheric scientists study the chemistry and physics of that vital envelope of gases that keep our planet habitable. Any rock or lithic material at the surface of the Earth is subjected to the chemistry and physics of the atmosphere. Oxygen and rainwater leach minerals right out of the rocks, or the metals found in rocks. We call this rust. Winds pick up small grains of lithic material, which that just means sand and dust, and carries them further away from their source rock than they could get on their own. But these interactions are not a one-way street. Geology also impacts the atmosphere. When volcanoes erupt, they send ash and all kinds of chemicals that are part of the interior of our planet up into the air. And this can have a big impact on greenhouse gases and the chemistry of rain, for example. Now, water is in every part of the cycle of rocks and has an impact on the geosphere. Glaciers carve huge U-shaped valleys into the bedrock. Rivers can carve steep-sided V-shaped valleys into the mountains they run down. Oceans tirelessly beat down the coasts of continents and slowly break them down. If you add water to a certain mineral, it might change into another mineral. Other minerals only form from evaporation of mineral-rich waters. This may be a rocky planet, but it's also the blue planet. It's a water planet. Oceans cover 2/3 of the lithosphere. Again, this is a two-way street, right? The mineral content, specifically the salts, determine the density and behaviors of columns of water. The kinds of mineral loads in lakes and rivers determine what can live around that water source. Plate tectonics form new oceans as plates pull away and destroy current oceans by lifting them slowly above sea level.
So, you have been watching the video and I'm waiting for your work to be checked. Thank you for your attention.